Hey everyone, so now we're going to be talking about conformations of carbon-carbon single bonds. There's a pretty big jump from naming carbon compounds, and this is where we're going to start thinking about compounds in a different way from a 3D spatial standpoint. Okay, so when we say conformations of carbon-carbon single bonds, what we mean is that what are the positions a molecule can assume by rotating around a single bond. Okay, and by conformations, that means the different arrangements forms by rotating about a sigma bond, right? That single bond. And something that'll be useful in thinking about this is something called a sawhorse structure, which we'll talk about in a second. And this is a representation of a molecule looking down at an angle towards that carbon-carbon single bond. All right. So looking at ethane, right? The simplest carbon-carbon molecule we can have. We have the hydrogens here shown for clarity. This will be really important in a second. And so if we rotate right around that single bond, right, we get a new conformation, right, seen here. So what happened, right? We rotated that carbon-carbon bond by 60 degrees. So this carbon, right, you see this, the way the arrow is drawn is showing it's rotating counterclockwise, right, kind of rotating towards the left. So this hydrogen, while it is wedged, right, remembering that wedged bonds means coming towards us out of the plane, that hydrogen is now over here and in the upward position, right, it's in the plane. Hydrogen number 2, right, it rotated 60 degrees, so it had to rotate downward. So now it is in this position. And hydrogen 3, right, again, we're rotating counterclockwise, so it ends up getting pointed towards us, so now it is wedged. Right now it is coming towards us. That back carbon didn't change. We just rotated the front carbon here, right? You see that? And what's important to know, right, is when we say rotate 60 degrees, right, we're thinking of it in terms of a circle, right? Remembering that a circle is 360 degrees. So if we rotate 60 degrees, right, that means we are rotating, right, by this much approximately, right, 60 degrees, right, 1/6 of a circle, all right? And so with this rotation, right, what's a different way we can look at this molecule, right, rather than kind of from this side-on perspective where we have to use wedges and dashes to represent where bonds are located spatially. So that's when we look at the sawhorse, right? See, this molecule and this molecule are exactly the same, right? This is just ethane, right, in the same conformation. And what we've done is we've just sort of rotated it a bit, right? We've rotated it to sort of point towards us. Right, see that? We've rotated this whole molecule so that the hydrogen, number 1, is kind of now to the right, hydrogen 2 is now kind of to the left, and hydrogen 3 is still in the plane and is pointed downward, right? And same thing with this back carbon, right? Take a second to sort of see that for yourself and prove to yourself that this is indeed the case, right? So this is a different way to look at ethane, right? We're just looking at it along, at an angle, right? And this middle bond here is very exaggerated, just to get that point across, right? That we're looking at it down from an angle. So if we rotate it by 60 degrees, right, and you can see the circle thing a little bit more clearly, right? We're rotating 60 degrees. So hydrogen 1 will go up, 2 will kind of go down, and 3 will kind of go over here to the right. See that? And this is exactly the same up top as it is down below. See that? I hope that makes sense. I hope that's clear. So sawhorse structures are great, you know, for a sort of quick glance at these sort of molecules, but there's a better way we can look at them, and that is called a Newman projection. All right, and this is going to be something we're going to be looking at a lot over the course of this semester and the next. So this is a way of drawing a molecule looking straight down the bond connecting the two carbons. So unlike with the sawhorse structure where we're looking at it from an angle, we're looking directly at the molecule now. Okay, so again, looking at ethane, same as before, and we're using this blue arrow here to indicate which carbon we're going to start looking at, right? So we're indicating this carbon is the carbon we're going to have in our focal point. So for this sort of front view, right, of ethane, this is what the molecule ends up looking like. See, we're taking this molecule and we're turning it towards ourselves, right? Remembering that hydrogen is pointing out at us, you know, towards us out of the plane. And this dash bond, right, hydrogen 2, is pointing into the plane, right? It's going back. So when we turn it towards ourselves, this is the representation, okay? And if you have a molecular model kit handy, I would suggest you build ethane like this, and then turn it towards itself so you can see that this is true. All right. And so with a Newman projection, you can see that there is a circle kind of drawn here, right? Similar to what I was saying before, and it helps us to sort of visualize the rotations that are going to be occurring with Newman projections, okay? And so to sort of break down what we're looking at here, right? There are still, of course, 2 carbons present here. The front one, right, is kind of right here, very similar to what this looks like. But the back carbon looks like it has, quote unquote, disappeared, but it hasn't. We're just representing it now with this larger circle that is behind this first carbon, okay? So we're going to break it down. Let's look at it like this. The front carbon will be in red, and the back carbon will be in blue, all right? See this front carbon right here, right? This is only the front carbon, okay? We're sort of dividing the molecule in half just to sort of piece it together, right? So you can kind of visualize what a Newman projection, what its components are, okay? So again, turning that front carbon towards us, right? The hydrogen is off to the right, this hydrogen 2 is off to the left, and hydrogen 3 is down, all right? And the back carbon, right, same thing, when we turn it towards ourselves, hydrogen 6 is off to the right, 5 is off to the left, and hydrogen 4 is up top. And then we're just stacking one on top of the other. All right, you see that? And we're going to get plenty of practice doing Newman projections, so hopefully these will get easier and easier to visualize and to draw for yourselves. So now let's rotate ethane by 60 degrees, and let's see what happens. And we're going to be talking about some terms here that'll be helpful for describing what we're going to be visualizing, okay? And so the 3 terms that we're going to be using here, one is dihedral angle, okay? This is the angle between carbon-hydrogen bonds on the back carbon and the front carbon, right? And so what do I mean by that? So the dihedral angle is, right, the angle between the CH bonds on the back carbon and the front carbon, like this. See that? This is the front carbon, and hydrogen 4 is attached to the back carbon. This dihedral angle, right? This dihedral angle is 60 degrees, okay? And so, remember earlier we were talking about conformations, right? And conformations differ when you rotate the carbon-carbon bond. So the 2 different types of conformations we're going to look at here is staggered, when the hydrogens on the back carbon are staggered halfway between those in the front, so the hydrogens have a dihedral angle of 60 degrees, right, just like here. This is typically the most stable conformation for molecules, okay? And we'll get into that in a second. So this is a staggered conformation, okay? The dihedral angle between those carbon-hydrogen bonds is 60 degrees. And so if we were to rotate this molecule by 60 degrees, right, rotating counterclockwise, now the hydrogen atoms are on top of each other, okay? Just like it's shown here down below, right? These 2 are the same structure, or the same conformation, rather, right? We can't have hydrogen like right on top of hydrogen 4 because that wouldn't look great, right? So that's kind of why it looks a little skewed here, just because we want to show it as close as possible for these hydrogens to be on top of each other, but having them right on top of each other will not make a good drawing, if that makes any sense. So what's the dihedral angle here, right? The dihedral angle here is 0 degrees, right? There is no angular difference between these 2 atoms, they're right on top of each other. So looking at the next description, this is an eclipse conformation, right? The hydrogen atoms on the back carbon are hidden, quote unquote, eclipsed by those on the front carbon, okay? These hydrogens have a dihedral angle of 0 degrees, and this is the least stable, higher energy conformation for molecules, right? And why is this a higher energy conformation, right? Why is this less stable? You can probably imagine, right, if the hydrogens are right on top of each other, or don't forget that atoms are just particles, right, with electrons and electron density. So if the atoms are closer together like this, there is more energetic repulsion, right? They don't want to be apart. So the staggered conformation is the more stable conformation for a molecule like ethane to want to take, okay? And take a second here again to look at the difference between the line angle formula, right, for a molecule and the Newman projection for a molecule, okay? Remember, these are identical, right? We're looking at this carbon here for this Newman projection, right? And of course the same for over here. So take a second and convince yourself that this is true, that these representations are the same, remembering that you have to rotate the molecule towards yourself, right? So this hydrogen that is wedged coming towards you is getting pushed to the right as we're taking this molecule and turning it towards ourselves, okay? So energetically, right, remembering that staggered conformations are more stable than eclipse conformations, what does this look like on a graph? Okay, so we're going to look at torsional energy strain of ethane. Okay, and what does torsional strain mean? It means the destabilization or higher energy of a molecule by an eclipsed bond. Okay, so torsion, right, remember, is sort of like a twisting motion, right? So if a molecule is always rotating, always moving, right, in solution or in space, the strain that it experiences through this torsion is going to be represented by this graph. Okay, and the destabilization, that higher energy from torsional strain, comes from an eclipse bond. So let's go ahead and draw that. We don't really care exactly how much energy it is. We just sort of care how much higher energy it is. Okay, so that's why the only sort of indicator here for energy is here at 0. Right, we're just looking at relative energy. Okay, so right, this first one here, right, for ethane, same as before, it is in a staggered conformation. So you know this is closer to 0. Then the molecule becomes eclipsed, like this. And it goes back down in energy as it becomes staggered again. And it kind of goes through the same motion over and over again, okay? And notice here, right, dihedral angle, okay? This dihedral angle is changing over time, okay? So we're saying, okay, the dihedral angle, let's say for hydrogen 4 and hydrogen 1. Okay, that's kind of what we're looking at. This here is 60 degrees, okay? Over here it's 120 degrees, right? And so on, all the way into the end where it is 360 degrees, which of course is equivalent to 0 degrees, okay? And even though it was 120 degrees for hydrogen 4 and 1, right, don't forget that hydrogen 4 and 2 are on top of each other, so the dihedral angle for that is 0 degrees, okay? This is just a way of saying that their molecule is rotating, okay? It's rotating by 60 degrees, 120 degrees, 180, 240, 300, 360, and then back again to 60 degrees, right? So take a second and sort of visualize this and see for yourself that this is true, right? That we are rotating this molecule 60 degrees at a time, right? Throughout this whole process, okay? So we have a couple examples here that we'll do together in class. I didn't want to do it here just because it would be, I think, better practice for us to do it together, okay? So the first one here is from the following Newman projection, draw the corresponding line angle structure, right, using wedge and dash bonds as we've been doing before. So take this and convert it, right, to a line angle formula. And for the second example, we're going to be filling out another torsional energy diagram, this time of propane rather than ethane, okay? And I've included some just bare bones skeletal structures of Newman projections, right? So you can fill that out on your own and get some practice with doing Newman projections. So if we're going to be doing propane, just to get us started here, right? Let's say we're looking at this carbon, okay? So we're looking down at the bond between this carbon, right, and this carbon, okay? So if we're going to do the first one at 60 degrees, it would look like, it would look like this, okay? So just like ethane, but of course there is now an extra methyl group, right, extra CH3 attached to it, okay? You notice I didn't draw any wedges or dashes here, right? I could put them in, but it is sort of extraneous information we don't need, right? Because hydrogens, right, we don't always include them, and they are, again, assumed to be there, and they are assumed to be in the right orientation spatially. So the wedges and dashes of hydrogens are here. They're just not represented here in a simple line angle structure. Okay? So go ahead and try to do this on your own, but we will do this together in class as well.